Assalamu alaikum and good morning. In the previous lesson, you have looked at writing the expression for equilibrium constant in terms of concentration. The symbol or the representation is Kc. Usually, to write Kc, we take the concentration of your products raised to the power of its mole ratio, P and Q shown here, over the concentration of your reactants, A and B, raised to the power of its mole ratio respectively. So Kc can actually tell us about the relative proportion or the relative amount of your products over reactants. Since we can simplify Kc as being products over reactants, the value of Kc can actually tell us the relative amount. So if your Kc is big, a big number, bigger than 1, like 10,000 or 20,000, that must mean the concentration of your products is much more than the concentration of your reactants. So we say that the equilibrium is shifted to the right or favoring the forward reaction. If your Kc is a small number, less than 1, and very, very small, like 0.005, for example, this means that the bottom number of your expression, which is the concentration of reactants, is high compared to the concentration of your products. So that means at this particular equilibrium, you have more reactants than products. Your equilibrium is shifted to the left. Or we say that the equilibrium is favoring the reverse reaction or the backward reaction. That's why you have more reactants in the system. You've also learned how to write down the expression of Kc. Now, I noticed that yesterday I accidentally wrote it as Kp for the equilibrium constant in terms of concentration. Whenever you see the square bracket, that indicates concentration. And whatever is inside the bracket indicates the concentration of that species. So for example, here, square bracket NH3 means the concentration of NH3 raised to the power of 2. And you notice that the number 2 is the stoichiometric number of ammonia in the equation. So please change for all the symbol that I used yesterday as Kp, it should be Kc, where C stands for concentration. You've also learned how to work out the units. If there's no units, you must write it as no unit. And please bear in mind, whenever you raise your concentration to the power of 2 or 3, that means the unit of concentration, mole per dm cube, is also raised to the power of the same number. And another thing to remember is that solid will not be included in your Kc expression, because also your Kp expression, solid will not be included, because Kc and Kp are based on concentration and partial pressure respectively, and we don't talk about the concentration of solid, nor we talk about the partial pressure of solid. Usually Kp would be for reactants and products that are in gas state. This is just an elaboration on how to work out your units. We've already done this yesterday, but if you feel like you need more practice, you can find some questions in the textbook, and in the exercise 7.1, there should be a few questions that allow you to practice working out your units. Today, we're going to do the calculations of Kc and Kp, and this falls under learning objective number 7 and 8. But before we jump straight into the calculation, we need to recall back the concept of Kc. Kc is the equilibrium constant based on the concentration of your reactants and products at equilibrium. Okay, so whether this is talking about concentration or number of moles, it has to be the value at equilibrium, because your starting value for reactants and your equilibrium value would be different. I'll show you the graph in the next slide. Usually the question will give you the initial amounts of the reactants and some other data, but you will have to work out the equilibrium amounts. It is extremely important that you use whether mole or concentration at equilibrium. This is the graph that I've shown you earlier in this topic. It's a concentration time graph of a reversible system that is achieving or going towards equilibrium. Initially, at the start of the experiment, where you have probably zero product and you have some amount of reactants, if you let the reaction proceed, initially they wouldn't be in equilibrium. They are still adjusting until up to a point where there is a constant, maybe here for your products, it reaches a constant concentration for the reactants and products. That's when equilibrium happens. So you can see the value of your concentration at equilibrium is the one that I'm highlighting now. So it's different. For reactants, it's different. And for products, it's a different number as well. Will it always be products higher than reactants? Not necessarily. We can also get reactants having a high equilibrium concentration than the products. But the most important thing is your initial concentration is the one that I'm circling right now. That is the amount or the concentration of your reactants and products at the start of the reaction. But when it comes to calculation of Kc, you are not supposed to use these values because they are not at equilibrium yet. So the value that you want to use is after equilibrium has been reached. And how do you know this? When there's no change in concentration anymore, your concentration stays constant. That's the value that you are going to use for your Kc calculation. What if you're not given it graphically? You're given in terms of just wordings where it says initially the concentration for the reactant is 1 mole per dm cube. Okay, and then at equilibrium, this is how much is left. Okay, so there is a simple formula that you can use. It's different from the graphical method. Okay, if you want to know the number of moles or the concentration of reactants at equilibrium, okay, you will take your initial minus how much have actually reacted. Okay, so not all your initial number would have been reacted, because if everything has gone into reaction, then you would be left with 0 at equilibrium. Okay, so take initial minus reacted, you get at equilibrium. This applies for number of moles. This applies to concentration as well. Now that's for the reactants. What about the products? Most of the time, you will start at having 0 product. Okay, you don't have product at all. So the expression is, or the formula is, the mole of product at equilibrium is equals to initial plus how much has been actually produced. All right, so the difference between these two is in the minus and the plus sign, because obviously if you started with initial 0 moles of product, you cannot minus anything to it, otherwise you will get a negative number. So for products that are 0 at starting at the start, you would have to add how much products you have formed, and at equilibrium would be the sum of that. Whereas the reactants, it's the opposite. You take the initial minus how much has reacted. Okay. Right. So we're now going to apply this idea or this formula into questions. The first question, we're going to look at example 4, which is on page 7. Okay. So you need to read the question carefully, whether they are giving you the initial amount or the equilibrium amount or how much that have reacted. Okay. Okay. So we've got a reaction between ethanol and ethanoic acid to form an ester and water. The reason why you need balance equation is because you will need the stoichiometry number or the mole ratio. Okay, 500 centimeter cube of the reaction, so that is volume. Remember, Kc is in terms of concentration, so that's volume. Of the reaction mixture at equilibrium, so that is good. If they mention at equilibrium, you can use the number straight away. You don't have to find anything else. Well, if they give you everything, of course. Contains 0.235 mole of ethanoic acid and 0.035 mole of ethanol, together with okay, 0.182 mole of ethyl ethanoate and 0.182 mole of water. Okay, so that's just telling you the equilibrium number of moles for the reactants and the products. Okay, use this data to calculate a value of Kc for this reaction and its units. Now, before we go to the Kc straight away, okay, don't jump to the Kc expression just yet. We first want to write down the concentration of each reactants and products at equilibrium. Okay, we're only given mole. We have to convert it to concentration. So I like to write or tabulate them. I'll start with the ethanol, C2H5OH, and then another column for the ethanoic acid, one column for the esters, and another column for water. Okay. I would just jump straight to finding the concentration. Make sure that the concentration is at equilibrium. Now, if you still remember your formula, concentration is equals to number of moles over volume. Okay, I will not use green because I noticed that it's not, you cannot really see the writing. Okay, so to find the concentration of ethanoic acid, to find the concentration of ethanol is 0.0350 mole per dm cube. Now notice that my volume is in centimeter cube. So that means I have to convert 500 centimeter cube into dm cube divided by 1000. So that would give me 500 divided by 1000, 0.5 dm cube. Okay, so this applies for ethanoic acid as well. The number of mole is 0.235 mole per dm cube. The number of moles of ethyl ethanoate, your ester in this case, is 0.182 mole per dm cube as well. Water is The same. Okay, you will work out the number, the concentration for each reactant and each products. Once you have concentration, then you move on to the expression. The question wants you to find the value of Kc. That means you have to calculate the value of Kc as well as its units. Okay, so let's write that down. Kc is equals to concentration of your ester. Just be careful before you write down the Kc expression. You have to ensure that all of these reactants and products will be included in Kc. Liquid, yes, they're all liquid. Okay, none of them is a solid. So concentration of my product, which is the ester, raised to the power of 1, because there's only 1 mole. They're all 1:1 ratio, so you don't have to worry about raising the concentration to a certain power. Okay, next is the concentration of H2O raised to the power of 1. That's your products over the concentration of your reactants, which is your ethanol, also raised to the power of 1 because the mole ratio is 1, times by the concentration of ethanoic acid, CH3COOH. Okay, to work out the units, same thing. On top, you have 2 brackets, so that's mole per dm cube times mole per dm cube. Each bracket represents a mole per dm cube. At the bottom, you would also have mole per dm cube, and they cancel out nicely. You will add in these numbers into the Kp expression correctly. Okay, remember that each bracket is multiplied, not added. Okay, you don't see a plus symbol there. So that means the concentration of ester is multiplied with the concentration of water, or ester times by water, ethanol times by ethanoic acid. Okay, so I want you to work that out and find the numerical value of Kc, and you have to write no unit. Okay, Kc, oh, the numerical number is there, 4.03, no units. So please try to work it out. Okay, see if you can get 4.03, right? If you want to copy down this working, you can pause the video here and then copy it down. I'm going to move on with example 5. Okay, so this example 5 is where it starts to get a little bit more complicated. Okay, so the answer is already there, 0.196, and it has no units. Okay, for the following reaction in a container of volume 600 centimeter cube, so that's your volume again, there were initially 0.5 moles of hydrogen and 0.6 moles of chlorine. At equilibrium, so you've got initial numbers and you've got equilibrium numbers, there were 0.2 moles of HCl. Calculate Kc and state its units. Okay, so you need to understand what these numbers are. Okay, unlike in the previous question, these moles are given to you at equilibrium. It was mentioned, right, at equilibrium. So you don't have to worry about it. You take the number of moles of equilibrium, you divide it by the volume, you get the concentration. Okay, that is the case when number of moles at equilibrium are given. What if there's only number of moles of HCl given at equilibrium? You cannot just simply assume that everything else will also be 0.2 moles. You have to follow a certain process or a certain working. So this is an example when not all mole at equilibrium are given, okay? So you notice that I've tabulated them. I've tabulated my reactants, H2 and Cl2, and then my product, which is HCl. And just so that you don't forget, write down 2HCl because that is the stoichiometric number of HCl in that equation. Okay, so what do we have here? So I would tabulate each reactant and each product according to its initial number of moles or initial value, how much have reacted for the reactants, and how much have produced for the products. And lastly, well, last for this part, okay, you can find out the values at equilibrium, right? Initial, reacted, equilibrium, IRE, and I call this the IRE table. The reason for this is when we looked at the first part just now, you can find the number of moles of equilibrium if you know the initial number or if you know the reacted number. Okay, you need to know 2 out of 3. 1 is not enough. Okay. So now I'm going to put down the information from the question. Initially 0.5 mole of hydrogen. So I've got it there written already. And initially 0.6 mole of chlorine. So I've got it there as well. There is no mention of product. That means there is no product at the start. Okay, so I will write down 0 mole of product when this reaction literally just started. Okay. Now, what else do I know? I know that at equilibrium, there were 0.2 moles of HCl. That HCl is my product. So I've already included the number here. Okay. I know for HCl, the equilibrium amount is 0.2 mole. Okay, so you can see that there are empty here. And there's an additional row that's for later on the next stage. Okay, so I just want to focus on the IRE. Now, can you see that I just said it just now? I have 3 information, 3 values, initial, reacted, and equilibrium. Okay, I need at least 2 information to get the third unknown value. So if you look at the column for HCl, I have initial 0 mole for the product. At equilibrium, I have 0.2 mole of product. So that means I can use one of the expression. So I will write down number 1 so you know where to start, okay? So first, I will work out the number of moles produced using this equation. Equilibrium for product is equals to initial plus produce, I plus P from here. I plus P. Okay, so I'm just going to leave out the mole. You can add it to your table and write down we are talking about moles. Okay, now from this expression, I know my initial, I know my equilibrium, so I can find P. Equilibrium minus initial. So if you take the equilibrium, 0.2 and initial you have 0, that means 0.2 moles of product have been formed. Okay, you may say, oh, that sounds a bit silly to use the expression, right? Now, it's not silly when things get a little bit more complicated. Okay, now, how much reactants and products that have actually been produced and used up actually follows the mole ratio. Okay, let's see. Right, if I just look at the equation, what the equation is saying, for every 1 mole of hydrogen that have reacted and 1 mole of chlorine that have reacted, it will produce 2 moles of hydrogen chloride gas. Okay, that's the exact amount. However, in this reaction, we did not get 2 moles of product. Instead, we get 0.2 mole. Now, in this case, the presence of the equation can actually tell us, if I know the product, how much product is produced, I can find my reactants using mole ratio. So this middle row is special. I usually give asterisk because this is the only row that can use mole ratio. Okay, you cannot use it for initial. You see, initially 0.5 mole reacts with 0.6 mole, and that's not a 1-to-1 ratio. In a reaction, 1 hydrogen should react with 1 chlorine, right? So where am I going with this? Mole ratio. Okay, step 2. Maybe I'll start with chlorine first. Okay, I know that the ratio between chlorine and HCl. Now, why do I use HCl? Because I have information about HCl. Okay, the mole ratio between chlorine and HCl is 1 to 2. Okay, because this is step 2, I know that what if I produce 0.2 moles of HCl? What is the number of moles of chlorine that must have reacted to get me 0.2? Okay, some of you may be able to see this quickly even without calculation. Chlorine is half of HCl. Okay, so that means you can do cross cancellation, right? But if not, you can just write it as 0.1 mole. Okay, so I purposely write down the values huge, okay, so that you know this is the numbers that I'm looking at, as well as this. The small handwriting, the small written part is your working. Okay, right, I'm getting there. I know how much hydrogen chloride is produced. I know how much chlorine I must have used. I now want to find number of moles of hydrogen, right? Using the mole ratio again. Same thing. Well, there's 2 ways you can look at this. Since you already know the number of moles of chlorine, and we know that chlorine and hydrogen is 1 to 1, so that means the number of moles of hydrogen reacted must also be the same, 0.1 mole. Okay, the reason is because hydrogen and chlorine is 1 to 1 ratio. Now that is not safe, because what if you didn't get your chlorine right? So everything will be wrong. Okay, so the safest is again to look at the relationship between hydrogen and hydrogen chloride gas. In this case, same thing, the relationship is 1:2, and we know that 0.2 moles of product has been formed, and how much of hydrogen must have reacted in order to get this number. Okay, again, cross cancel. You should get that number of moles of hydrogen reacted is 0.1 mole. Okay, so now your second row is done. That's easily done because you can use mole ratio. But that's not enough yet to do our calculation for Kc. We need the concentration at equilibrium. At the moment, we're still at number of moles, right? If you still remember from this page, to find the number of moles of reactant at equilibrium, E is equals to initial minus reactant. Okay, so to know how much is left at equilibrium, you need to know how much you started with and how much you have used to produce your reactants, right? So that means the third row is, I'm going to number them 4, 5. Okay, they can be interchangeable. You can deal with 5 first and then followed by 4. Okay, it doesn't matter. So at equilibrium, you need to take initial amount minus how much have reacted. So that makes sense, right? That tells you how much is left in your system, left in your equilibrium. So your initial for hydrogen is 0.5 minus reacted 0.1 mole. So the answer is 0.4, oops, 0.4 moles of hydrogen at equilibrium. Whereas for chlorine, same thing, at equilibrium, how much chlorine is present? Again, you take the initial of chlorine, not of something else. We're talking about chlorine here. So that means initial is 0.6 minus reacted 0.1. So that means it's 0.5, okay? 0.5 mole. All right, we've got all the number of moles at equilibrium, okay? But case C, the C stands for concentration. So we have to add another column to find the concentration at equilibrium. So this is the same as the previous question. Using the formula N over V. Okay, so our volume initially was 600 centimeter cube, and if we change that to dm cube, we divide it by 1000. So just add on, it should be 0.6 dm cube. So this is where sometimes writing down the units will come in handy. Okay, right, so concentration at equilibrium 0.4 over 0.6. If you want to write down maybe like this. Okay, the next one 0.5 over same volume because they're all in the same system. And lastly 0.2 over 0.6 mole per dm cube. Okay, then only you can move on to the Kc expression. Kc is equals to the concentration of HCl. Just make sure that all your reactants and products are not solid. None of them is a solid. Okay. Okay. Next, HCl, right? Don't forget, raised to the power of 2. HCl raised to the power of 2. I know I have omitted the state symbol over the concentration of your reactants, H2 to the power of 1, Cl2 also to the power of 1. Okay, so just to remind you again that these brackets indicate concentration. If you know, if you're wondering what that square bracket is. Just sub in your number, check if using that expression can give you 0.196 as the answer. No unit, I'm going to show you how to get no unit. So top part, you've got mole per dm cube squared. Okay, bottom part, mole per dm cube times by mole per dm cube. So that is essentially squared as well. Okay, so bottom part cancel, sorry, top and bottom cancel out. So that's how you get no unit. Okay, make sure you mention your answer as no unit. Now, even though I've already given you the example here, you need to work out and see if using that expression will give you 0.196. Okay, right. If you want to copy this down, you can pause here and then I will move on to the next question. Next question, example 6. Propanone reacts with hydrogen cyanide as follows. So we've got propanone reacting with hydrogen cyanide to form a hydroxynitrile. Okay, so this is a hydroxynitrile product. This is an equation or a reaction that you have visited in organic chemistry. Okay, so it is a nucleophilic addition reaction. Okay, a mixture of 0.05 mole per dm cube. So this time it has given you the concentration. So you don't need to convert it to number of moles. Okay, so you can write down concentration is given. However, we still don't know if the concentration is at initial equilibrium or how much have reacted or produced. Okay. A mixture of 0.05 mole per dm cube of propanone and 0.05 mole per dm cube of hydrogen cyanide is left to reach equilibrium. That means it hasn't reached equilibrium yet. These numbers that are given to you are initial concentrations. Okay, it's very subtle there, but if you try to read the question again, they are left to reach equilibrium. That means they are not at equilibrium yet. Okay, not at equilibrium yet. At equilibrium, that is definitely an equilibrium. Okay, at equilibrium, the concentration of the product is 0.0233. Okay, so this one is familiar to similar to the previous question. Okay, so if I were to now the tables are not prepared for you in the exam. Very rarely you will see that they prepare the table for you. This table is should be your own initiative. Okay, you prepare your own table. Of course, in the exam, please don't waste a lot of time on preparing the table because that's not what you will be awarded marks for. Okay, they are more interested in your working and your final answer. Right, at equilibrium, the concentration of the product. So again, same thing, I have my reactants, columns for my reactants, propanone and hydrogen cyanide. And then I also have a column for my product. And conveniently, they are all 1-to-1 ratio. So I just write down, or, don't have to write down the number here. Each row consists of initial, reacted, or produced, depending on who you are looking at, and equilibrium. Okay. Now, I'm going to fill in my table, the table that I've prepared for myself. Propanone, I started with 0.0233. 0.0500. And I've also started with 0.0500 hydrogen cyanide. Maybe I'll refer to my notes. And no mention of my product initially, so that must have been 0. At equilibrium, I have 0.0233 moles per dm cube of product. Okay, so maybe you can write down the units at the top left corner of your table. Okay, just to remind you again that these are not moles, these are already in concentration, so you don't have to convert them. Okay, if you look at each column, you only know one value or one information about your propanone. Same goes to your hydrogen cyanide. You only know one information, so there's not much you can do. Whereas for your product, you know your initial and you know your equilibrium. Okay, so you can use your IPE expression. And in this case, at equilibrium is equals to I plus P. Okay, you want to find out P, so you rearranged. P should be equals to E minus I. And conveniently, your initial product is 0. So that's just that just means that the number you have at equilibrium is also the same number that you were produced because you started from 0, right? So number of moles of product produced is 0.0233. So I've purposely left out the units of concentration because I've already put everything on the top left of the table. Okay, so that's done for my product. I now need to focus on my reactants. Okay, I will just number them here so you know later on when you do the question, you know where to start first. Now, the special thing about the middle row, as you would notice that I usually write an asterisk there. Only in this middle row that you can use mole ratio to work out about other people. Okay, you usually work out your initial, reactant, and equilibrium of yourself. But the special thing about reacted and produced is that if you know the mole ratio, you can work out this middle column. Okay, right. So I want to find HCN first. Again, there's no really strict rule saying you have to find HCN first or you have to find the propanone first. Okay. Second step, I want to find the number of moles of hydrogen cyanide based on the number of moles of hydroxynitrile produced. So looking at the mole ratio, HCN has a mole ratio of 1:1 with the product. Okay, this is gonna be super long. I should have, okay, never mind. So the mole ratio is 1:1. If I have produced 0.0233 mole per dm cube of product, how much or how many moles of HCN should have reacted? Okay, so it's a 1:1 ratio. That means it's the same, right? And I think you can see the pattern here. Next step, you can choose to find the concentration of hydrogen cyanide at equilibrium, or you can find the concentration of propanone that has reacted based on the mole ratio. That is totally up to you. Okay, to be consistent, I would just work out the number of moles of propanone that would have reacted to produce 0.0233 mole per dm cube of product. Okay, so again, I have to look at the relationship of my propanone to my product, CnCH3. And it turns out that they are nicely 1-to-1. Same thing, if you produce 0.0233, how many propanone or how much propanone would have reacted? It is a 1-to-1 reaction, so it's 0.0233. Okay, step 4 and step 5 is working out the concentration at equilibrium based on the initial, how much have initially reacted or how much you started with, and how much reactant has been reacted in the reaction. Okay, so to find E, I'll change the E is equals to I minus R. So if you want to find the equilibrium of HCN, you should stay inside the column of HCN. Don't use other people's value. Okay, so that happens to be 0.05 minus 0.0233, and that should give you 0.0267. And then same thing for propanone as well. The concentration of propanone at equilibrium should be initial minus reacted. So that's 0.05 minus 0.0233. So to give you 0.0267. Now it is just a coincidence that the concentration of the reactants at equilibrium is the same, but this is not always the case. You don't assume, oh, because they're 1-to-1, that's why the value is the same. No, because the initial concentration is the same, and then how much have reacted is the same because of 1-to-1, right? That is correct. And of course, at equilibrium, you also have the same amount, but you don't necessarily have to have the same amount. Clearly, you can see from the previous question where your reactants don't have the same amount and the total of your reactants does not equal to the total of your products. That's a common misconception. Okay, right. I am already in mole per dm cube, so I don't have to worry about the conversion. I just have to worry about my Kc expression. I'll use a different color. Kc is equals to the concentration of products. In order to get the mark, sometimes you have to write down the Kc expression. I know how eager you are to just put in the numbers into, top divided by the bottom number, and then you get the answer and write down the units. Try to make it a habit to always write down the expression based on your reactant and products. Okay, so concentration of product is raised to the power of 1 because the mole ratio is 1 over concentration of reactants multiplied together, and each of them has a power of 1 because of the mole ratio being 1-to-1. Put in the numbers, okay, and you should get 32.7. Okay, if you don't get that, that means there's something wrong with your calculation, or maybe you put in the wrong number in your calculator. Next, I want to work out the units. So top part of your expression, you've only got one bracket. The concentration is for one species, so that's just mole per dm cube. Next is the units for the bottom part of your expression. There are two brackets. mole per dm cube times mole per dm cube. Okay, and they cancel out. So I've shown you this already. We don't usually leave our notes in 1 over something, 1 over mole dm cube like that. We bring the units up, and when we do that, the sign changes. Your mole now becomes mole minus 1. Your dm now becomes positive 3. So you can either write it as mole minus 1 dm cube or dm cube to mole minus 1. Don't get confused, right? So if you want to copy down this working, I don't know if you can see it, but I hope you can. I will try to squeeze most of the things here. Okay. Is there anything there? No. Okay, don't forget to work out, put in the numbers. I've already given the answer to you. All you have to do is just try and see whether you get the numerical answer or not. While you are doing that, you can pause the video here and I will move on to the next question. Okay, that looks like the last question for this for KC exercise. Example 7. For the following equilibrium, initially, so that's a keyword, initially there were 1.5 moles of nitrogen and 4 moles of hydrogen in a 1.5 dm cube container. So that is your volume, and nicely it's already in dm cube. At equilibrium, 30% of the nitrogen had reacted. Okay, this is the confusing bit because it says at equilibrium and then it says had reacted. What does that mean? Is it reacted or is it equilibrium? Okay, now let's fill in the other information that we know and we are sure of first. Initially, 1.5 moles of nitrogen and then 4 moles of, okay, remember this is mole, right? That means we need to do an extra step to convert the mole to concentration. 4 moles of hydrogen, no mention of moles of the product, so I'm assuming they started with 0 product, okay? At equilibrium, 30% of the nitrogen had reacted. This means that only 30% of the initial was involved in the reaction. The rest, in a way, the one in excess stays in your equilibrium. Okay? So that means your first step is 30% of 1.5. That means not all 1.5 will go into reaction. So 30% of 1.5 is 0.5. Okay, so I'm just going to write that as big as I can. Let's see, just to remind ourselves of the equation, 1 mole would need to react with 3 moles of hydrogen to form 2 moles of ammonia. Okay, so this time you know the reacted. You don't know anything about produced. You don't know anything at equilibrium. Now, if you notice the first column, the column for nitrogen, we know 2 out of 3 values. Okay, so that means to find the number of moles at equilibrium, you take initial minus reacted. So your initial is 1.5 minus 0.1. 0.45. Okay. So that means the answer is 1.05. Actually, if you didn't do this first, I'm gonna put that aside first. Okay, there's nothing wrong with that. But your second step can be here. Remember, something special about this middle row is that you can use mole ratio to find the value of other people, as long as you know the relationship. How? If I want to find the number of moles of hydrogen, I need to know the mole ratio of nitrogen and hydrogen. Their relationship is in 1:3. So if I reacted 1 mole of nitrogen, I should have reacted 3 moles of hydrogen. If I reacted 0.45 moles of nitrogen, how much mole of hydrogen must I use? So that's one of the most important application of your mole ratio. Okay. So that means it's 0.5 times 3, 1.35. Okay. Next, if I know, again, I know the mole ratio of nitrogen and ammonia, and I know how much of nitrogen have reacted. So I can produce the, I can count the product of, the number of moles of the product. Okay, so I'm going to start with nitrogen to ammonia is 1:2. If your nitrogen was 0.45, how many moles of ammonia would you have produced? And this turns out to be 0.9. Okay, so try to separate your working and your answer so that you don't get confused. Your answer, write it as big as possible. Okay, so that's step number 3. Step number 4 is to find the value at equilibrium using initial minus reactant. Likewise, to find the number of mole of reactant, the second reactant, which is hydrogen, you take I equals to, you take E equals to I minus R. So that means initial is 4, reactant is 1.35, you should get 2.65. So again, this is an example that tells you the reactants don't always have the same number. Okay, products. Step number 6, products is a little bit different. At equilibrium, it should be initial plus produce. Okay, so that means 0 plus 0.9, you should get 0.9. Yep. Is there any answer for this? 0.0927. Okay. So these are still number of moles. I've omitted the units, but if you think it would benefit you if you add on or write on the unit, of course, that is not wrong. So we need to convert your number of moles to concentration. And thankfully, your number of moles of equilibrium have been found for all 3 reactants and products. Okay, concentration at equilibrium. So that's important. You don't just use initial concentration or how much concentration of that species has reacted. Okay, to find concentration, number of moles over volume, the volume here is 1.5 dm cube. So 1.05 over 1.5, 2.65 over 1.5 dm cube, and 0.9 over 1.5 should give you mole per dm cube. Okay, so mole dm cube, just to make yourself get into the habit of writing the units so that you know, oh, it's the mole divided by the volume and it's not some nonsense number. Okay, next step is pretty straightforward. You want to find Kc. You take the concentration of the product, in this case is your ammonia, raised to the power of 2, divide by the concentration of one of your products, which is nitrogen. It's only got 1 mole, so you multiply it by 1. Concentration of hydrogen raised to the power of 3. Okay, following the mole ratio. To work out the units, since your bracket is squared, your unit must also be squared. At the bottom, I've got 1 squared multiply, 1 mole per dm cube multiplied by that. The other one is mole per dm cube to the power of 3. Okay, cube. You can cancel anything that can be cancelled. So you have 2 on top. That means at the bottom, you're left with only 2. So that gives you 1 over mole per dm cube. Carry it up. I'm going to continue at the bottom. Mole minus 1 dm cube. Hey, sorry. There we go. I've made a mistake because I left out the square there. Okay, and I bring it up. At this point, you can open the bracket. Okay, maybe you open the bracket first, but if you can't see it, then that should be fine. Mole square dm minus 6. Okay, then you carry it up, it becomes mole minus 2 dm 6. The minus 2 should go up. Sorry, I drew it too big. Okay, mole minus 2 dm6, or there's another way of writing this down, dm6 mole square. Please put in the number into your Kc expression and see that you can get the numerical answer of 0.0927. Okay. Right, the next one will be Kp. Okay, so please be reminded to change the expression. Last time I wrote Kp instead of Kc. It should be Kc, so please change that, okay? I will not continue with Kp today. I will do Kp in the next lesson together with the calculation, okay? Right, don't forget, let me just show you to the last example. Don't forget to work out these questions, put in the numbers and see whether you can get the numerical answer or not, okay? Please be reminded to fill in the questionnaires on Microsoft Forms. Assalamu alaikum and thank you.